first of two meetings. The second one is on the 17th of November, catering or in a time catering different time zones for Australia and Asia. I'm Asbjørn Robjersen. I'm a co-convener of the Bias Methods Group, along with Isabelle Boutron and Julian Higgins and Matt Page. And Camilla Hansen Nightscore is the BMJ Research Coordinator, who will guide us through the technicalities of this meeting. So the agenda is that we have 10 minutes for a short presentation of the group activities last year. Then we have 10 minutes presentation by Isabelle Boutron and Julian Higgins on the involvement of the Bias Methods Group and Robin's eye on WHO work on effectiveness of vaccines against COVID-19 variants of concerns. And then a longer in-depth presentation by Professor Jonathan Stern on the biases in observational studies of COVID-19 vaccines. And we have 10 minutes for discussion and comments. And if you have questions and comments, please click on the reaction button and press raise hand or use the chat function. And we will open up at an appropriate time. So without further delay, the chat button is down usually at the bottom, and the reaction button is there as well. So, Bias Methods Group, we have roughly 350 members, quite an active Twitter account with 2,262 followers, and the BMJ website activity has been roughly with 65,000 visitors. These numbers are stable over the years and growing slightly. So we've had 5 teleconferences and sent out 1 newsletter, but I'm going to focus on our main activities, the ROB2 training and development process, the working we have doing on new tools, and some other projects. So during the year, 2 new versions of ROB2 were made available on riskofbias.info. A test version of the cluster randomized trial version is available. Last, I think it was revised in March, and a test version of the crossover trial version also revised in March. And these 2 versions of ROB2 complement the main version focusing on parallel group randomized trials. However, a main activity of the group has been on the implementation and training of the Risk of Bias tool too. There has been a number of webinars hosted by the Cochrane Training, and some of these webinars were held last year, but at least 3 or 4 of them were held in 2020, 2021. For example, Jelena Savovic on reaching an overall risk of bias judgment, and Matt Page on domain 5 bias in the selection of the reported result. Besides that, there's been considerable activity on risk of bias missing evidence in research synthesis, ROB-Me, which a primary version is available in riskofbias.info. And I think Matt is very keen on getting feedback, so you're very welcome to have a look and try it out. Tool to address conflicts of interest in trial Tacit is under developing. You can visit the Tacit website. It's under user testing now. We expect that it'll be released in a preliminary version during next year. Robin's E is close to finish, I hear, and questions can be asked to Julian and Jonathan. We I've had some other activity as well. The COVID network meta-analysis initiative led by Isabel the group has coordinated development of training material for risk of bias 2 assessments for those specific COVID-19 trials, and running a quality control of ROB2 assessments. Besides that, there has been activity, more peripheral activity, but on reporting guidelines, both Spirit and CONSART are under revision, and PRISMA 2020 was published, I think it was in January this year. Our plan for activities 2020 or the next year is basically to continue our focus on implementation and training of risk of bias 2, and further the development of ROB-Me and TACIT besides the other activities I sketched. So, any questions, comments, feedback? Just or we can, if you potentially, we can also take them at the end. Okay, I see a chat here. I can't unmute myself. No, should have said that. Camilla is the unmuter, so she will unmute you. Okay, then I will pass on the word to, I think it was Isabel who will start.
Okay.
I'll just stop there.
Can you see my screen? Oops. You can't see anything, right?
Yes, we can see.
You can see my slides?
Yep.
No, we couldn't see the slide when you went to full view.
Okay. Can you see it now? Nothing?
No, just your pretty background.
Okay. I did partage. And now?
Yes.
Okay. Sorry about that. So I'm going to give you an idea of the main output of the COVID NMA initiative and present the protocol that we started with June Higgins and his team on observational studies assessing effectiveness of vaccine. So just as a reminder, actually the COVID NMA initiative, it's an international initiative that is a proof of concept of a new evidence ecosystem that was proposed by Philippe Raveau. And we did 3 papers in the Journal of Clinical Epidemiology describing this new evidence ecosystem. At the beginning, it was sort of a proof of concept to see whether it worked. And this system relies on 3 main pillars: a living mapping, a living systematic review, and a living monitoring feedback. And I'm going to describe only the living systematic review. So the idea for the living systematic review is to inform stakeholders from the beginning of the pandemic. And so we set up a platform, and we set up a complex process to be able to search every day for study with results, to extract the results out as soon as they are available. And as soon as data are extracted, we assess the risk of bias. And once a week, we do the analysis and produce for each comparison existing forest plot, summary of finding tables, and evidence profile. And all this is made available to the community. For this, we developed a living protocol. All data, of course, extracted in duplicate with consensus, and we go back to authors to request the missing data. All our results are made available on a platform, the covidnma.com platform. And you can see here for the living mapping, we identified and extracted data from 3,662 trials. And for the living evidence synthesis of published study, we have data available publicly for 547 studies. For all these studies, people can access the study general characteristic, a detailed risk of bias assessment for all outcomes with justifications, and the forest plot for all the comparison and outcome of interest. So currently on the platform, more than 1,200 forest plots are available, and we produced more than 4,000 forest plots since the beginning, with about 300 comparisons that are on the platform. For all comparisons that include more than one trials, we have a summary of finding tables. We also developed some tools, and this tool has been developed by Anna Shemani, MetaCovid. It's a tool where anyone can use the data that is available on our platform and perform their own analysis. So for example, they can decide, because currently we're presenting only results, the forest plot are only with random effect. They can decide to explore the data and use a fixed effect. They can focus on specific population, do subgroup analysis, and for example, decide to exclude high risk of bias studies. And they can download their forest plot and use their forest plot. So overall, this process has been successful. If we think about the process overall, I think it was successful because we had a very large scope. We're considering all randomized controlled trials of any treatment and any preventive intervention for COVID-19. So it could be drugs, it could be vaccine, it could be also non-pharmacologic treatment. What was very important was the speed for updating results. So we update results weekly. For this, we had to set up a very strong process, and like if you want an industry where each team was responsible for a specific task, and we did this in strong collaboration with Cochrane Response. We need to develop automations. We did start, but it's still semi-automated. But for example, part of the forest plot are automated. And we need also to question the methods we're using and try to improve the methods that we're using. So for example, we initially were trying to search data from all electronic database, but the LOVE platform with Epistemonikos did a wonderful work, and we evaluated this platform that allowed identifying 100% of randomized controlled trials and observational study for COVID. And so we stopped our search strategy and now search mainly in the LOVE platform, which reduced considerably the workload. We also had to develop a preprint tracker in collaboration with the CNRS to identify all updates and publication of preprint. Speed is important, but quality control was essential. And the bias method group was key in this task, because we organized with the bias method group a process where a random sample of our assessment was evaluated by a member of the bias method group with feedback, and this allowed considerably improving our process. And we also rely on crowdsourcing, because people are contacting us when they find something that is not appropriate. So initially, our process was dedicated to randomized controlled trials. From the very beginning, we also included observational study because there was no evidence available from randomized controlled trial yet. But very rapidly, we moved from this observational study to focus only on randomized controlled trials. We decided to extend the process to observational study for vaccine effectiveness, to assess vaccine effectiveness on variant of concern. First, because it was a request from the WHO saying that decision maker really need information about the evidence on these questions. And also because we were at the stage where we had only very limited evidence from randomized control trials. Most randomized control trials were conducted before variants arose. And on contrary, we had a lot of very large observational study based on routinely collected data that could be very informative for decision makers. And so we set up a strong collaborations with Julian and Julian Higgins and his team from Bristol. And we had to develop a protocol, and of course we encountered quite important methodological issues. First, the eligibility criteria. We had to think of how we can do to avoid being completely overwhelmed by all terrible observational study and be able to provide informative evidence. So we set up some strict eligibility criteria: comparative observational study, accounting for any confounder in of analysis, and reporting one critically important outcome. We also had an important issue related to the search strategy, because very often the data are coming from indirect evidence, meaning that we are extrapolating the exposure on the variant of concern from the prevalence of the cases during that time. And sometimes it was clearly reported in the observational study, but we also had a lot of observational study not stating anything about the prevalence of the variant of concern at that time. So we had to rely on specific sources and to determine the exposure on which variant of concern during the time of the study. We also, of course, have issue of overlap, because several studies can come from the same data source. And so it might not be exactly the same patients, but part of the same patients could be included in 2 observational studies. We also had important heterogeneity in the result presentations, because the same outcomes was analyzed in different ways. So we had to set up a process to make sure that we extract the data and choose the outcome consistently. And finally, we had to assess the risk of bias for the outcomes we are considering. And I'm going to leave this to Julian to detail our process.
Thanks, Isabelle. So I'm just going to say something about the risk of bias assessment aspect of this project. Just to introduce that, oh, that's the wrong slide. We have a fairly large team from Bristol, Public Health England, from Isabelle's group, and from Rome. And I've listed them here, well, the wider team, including those in the steering us. Each study that we receive from the systematic review team that Isabelle leads, we assess by 2 people independently, used to in systematic reviews. And we have on top of that a weekly team meeting of the full team, where we bring all the unresolved issues from those consensus meetings, and we use that to make sure that everybody is experiencing the sort of issues that everyone's facing, so that if they face those issues, they can know how we as a team like to assess things and try and get the assessments as similar as possible when the same issues are arising across all the people doing these assessments. Obviously, the tool we're using is the Robbins tool that we developed some years ago through the Bias Methods group. Risk of bias in non-randomized studies of interventions. It was published 5 years ago in the BMJ, and I'm sure many of you will know it, some of you may not. It's structured around 7 domains of bias. Bias arising from confounding, in how people are selected into the study or the analysis, how the intervention is classified, whether there are departures from the intended intervention, bias due to missing data, due to measurement issues around the outcomes, and in essentially cherry picking results for reporting in the articles. The published version, of course, is a bit old, and we, of course, as with the case with all of these tools, we recognize that things can always be improved. And we have been working for some years on both extending Robin's Eye to address more than the follow-up cohort studies that the published version focuses on, and also actually updating the central cohort version of the tool. And that has been happening in parallel with our development of Robin's E that Asbjørn mentioned earlier, which is very, very nearly ready now. We've made quite a few tweaks as we've developed Robin's E, and we are translating those back, as it were, across to Robin's Eye. So the new generation Robin's Eye will be very similar to the brand new Robin's E. And so some of the changes that we're making are revising signaling questions to make sure that they really address specific issues as simply as possible and are comprehensive. We'll be introducing algorithms, as many of us are used to for Rob2, as a way to map the answers to those signaling questions onto proposed risk of bias judgments. We think that we've made some simplifications to some of the domains. For example, in confounding, we'll almost certainly have some preliminary questions to map to very high risk of bias, so that we don't have to go, so that we can stop really early. We've often talked about screening questions, and we've actually got some drafted now to map straight to very high or critical risk of bias, so that we don't need to worry about all the other domains if one of them is really so bad that we shouldn't bother with the study. We've improved our framework for thinking about the actual confounding factors, and we think we've got a much better way of addressing immortal time bias. This is just an example of the sort of algorithm that we are developing, some of them more complicated than we're used to seeing for Rob2. This is the algorithm proposed for, this is actually the Robin's E1. This is what I expect it to look much like for selection bias. For this project, in the COVID-19 observational studies, we're using an interim update of Robin's Eye. It's not the same as the published one, and it's not quite how the major revision will look. But we're also using a version for case control studies that we have developed. It still needs a lot of work, but it's, I think, working for us when we encounter the case control studies, and particularly test negative studies are a particular type of case control study often used in vaccine research, and a lot of them in the COVID area. I think Jonathan may mention those. So I'm not going to talk about the actual bias issues we're facing, because that's why we've invited Jonathan to speak, but I thought you might be interested in a quick glimpse of the latest results. This is a forest plot directly from the platform, covidnma.com, and this lists the results we pulled out for the effectiveness of the RNA-based vaccines, which is essentially Pfizer or Moderna, against the Delta variant. And if I just explode the actual results, I think the news is really very, very good that these vaccines are highly effective against the Delta variant. The follow-up, I don't know if you can see in the fourth column, ranges a fair bit. Some are quite short, only a month, but a lot of them are 6 months or longer. The total amount of follow-up in the cohort. And then very quickly, you may be interested in the Oxford AstraZeneca vaccine or the Janssen one. Here are results for AstraZeneca, much very similar to that of the Pfizer and Moderna. Results not quite as promising for Janssen, but still certainly an effective vaccine. So I know this isn't about methods really, but I'm sure many of you right now are interested in our conclusions. There are certainly risks of bias, many serious risks of bias that Jonathan will talk about, although we do think generally a lot of the large studies have done a pretty good job with the sort of data that they're able to collect. It's very difficult to predict the directions of the biases because there are biases working in different directions, but we do not think the biases are at all large enough to detract from these very large effectiveness estimates that we're seeing. So we're concluding right now that there is really very robust evidence of the very high effectiveness of most of these vaccines against the Delta variant. Okay, great. I'll stop there. Asbjørn.
Yes, I was just going to unmute. Thank you very much. There was a single question.
From Tess?
From Tess, I think it was, yes. Camilla, can you unmute Tess?
Yes, just a second. Hi, thanks for that talk. It was great, Julian. I just wondered that were any of the studies you looked at, were any of the results from them at critical risk of bias? I guess maybe Jonathan's talking about that next, but I just wanted to ask.
Yeah, I can give a very quick answer. I don't think Jonathan's talking about actual Robbins eye assessments. So I can respond. Two parts to that. One is that we excluded studies that didn't attempt to address any confounders. That we probably would have been mapped to critical risk of bias if we decided to include them. So that's one answer. The other answer, the more direct one, is that yes, there is one result, I think, in our whole set of, I think about 200, almost 200, over 200 risk of bias assessments altogether now across the studies, that we assessed to be at critical risk of bias in the confounding domain.
Brilliant, thank you.
I don't remember a lot more than that about exactly why we did that, but we did.
Okay, great. Over to you.
Julian, did you answer the question about case control?
Well, I'm wondering whether that was asked before I mentioned it. I think it was asked before I mentioned it briefly in my talk, that we've got a version that's working well enough for us in private, but it's not one I'd want to share. We've still got some thinking to do, and I'm sure Jonathan would be happy to elaborate on that too.
I would not be happy to elaborate it. I mean, so Jane, the answer is, the good news is that there's a version in process. The bad news is that process has been going on since 2016 and has been even further slowed by the pandemic, I'm afraid. So we're not making any promises with that. Hopefully you can see my screen.
Yes.
So yeah, here's the talk that I was given, and I gave a version of this to the FDA when they were considering whether to introduce a booster vaccines, and the FDA, I mean, it's incredible because everything is public, and so there are thousands of people watching. I got messages from people I hadn't been in contact with since the 1980s, you also got rapid independent peer review. So this was from an article in Stats News where they talked about a long series of slides. The message, given so softly it could be missed, as Stern showed slide after overcrowded slide, was that vaccine efficacy may be holding up better than expected. So Julian's already showed you that vaccine efficacy seems to be holding up, and I'm afraid that you're now going to experience the slide after overcrowded slide. So this is work in particular with Miguel Hernan, Will Hume, Fiz Williamson, Elsie Horn, Millie Green, Tom Palmer, and Ben Goldacre. At least, so both on the methods, but also on the applied example I'm going to be showing you. And the work we've done is using data from the Open Safely Trusted Research environment, which contains data. I mean, it was established extremely rapidly in response to the pandemic, and it operates inside the data systems for England's two major primary care electronic health record providers, TPP and EMIS. And it's set up in a way that ensures that, well, with extremely secure approaches to ensuring, to respecting patient confidentiality, so that every access to raw data is logged and open, and that most code is developed against synthetic data, and only when it's completely ready is it run against secure data, but with very stringent output controls. And they produced really, really important work very rapidly during the last year or so, more than a year now. My examples are therefore from analyses of English data, but they're here to illustrate general issues in trying to estimate vaccine effectiveness from observational data. So I'm going to talk about a number of methodological issues in estimating effectiveness of vaccines in the context of the rapid rollout in high-income countries of COVID-19 vaccination. And Julian's already mentioned Robbins eye, one of the innovations when we published Robin's Eye in 2016 was to center the risk of bias assessments on the concept of a target randomized trial. The randomized trial whose results we are trying to estimate using the observational data. And here's one of the slides we use when we're teaching. The idea of a target trial is that it need not be feasible or ethical, but by specifying the target trial, that allows us to think, that defines what would be low risk of bias in our non-randomized study. So I think one of the reasons that it's so difficult to assess risk of bias, and it's so difficult to assess, the quality of the evidence from non-randomized studies of the effectiveness of COVID-19 vaccines, is because it's pretty hard to think about what is the target randomized trial. So back in 2020, everything was very bad except for one thing, which is that it was straightforward to design a randomized trial of COVID-19 vaccination. Lots of volunteers, people like Professor Julian Higgins, put themselves forward to receive to be randomly assigned either to one of the new vaccines or to either a placebo or to an alternative non-COVID-19 vaccine. And then they were followed up for symptomatic COVID-19 during 2020. And as we all know, those trials provided convincing evidence of very high efficacy against severe COVID-19 outcomes. So that's what we would like to do when we when we analyze observational data, is that we would like to estimate the results from a trial that we would get from a trial like that. But the problem is that sort of a target trial where we get eligible people, and at the moment we assess them to be eligible, for example, because they've not had COVID-19 and they're in the right age group and they haven't got any of the exclusion criteria, and then we assign them to vaccination or no COVID-19 vaccination at that point, isn't a good fit for the observational data that we have available. So this is my first slide from Open Safely, looking at the rollout of vaccination in England in people aged 80 plus in the top panel and 70 to 79 in the lower panel. And you can see what you already know from all of your countries, which is that vaccination rollout has broadly been an incredible achievement of health systems and a tremendous success. So in the UK, vaccination with Pfizer began on the 8th of December 2020. So here, Pfizer is the purple areas. So everybody starts off unvaccinated, of course, and then vaccination with Pfizer began on the 8th of December 2020, and vaccination with AstraZeneca began in early January 2021, and uptake was incredibly rapid. And then similarly, the vaccination became available to the 77 to 79-year-olds in early January. By then, the UK was using more AstraZeneca than Pfizer. It's not important to this talk, but in the UK, a small number of over 80s received second vaccinations within 3 weeks, but then the UK changed its vaccination schedules and decided on a minimum of 8 weeks between first and second vaccinations, which is why you don't see second vaccinations with AstraZeneca during this follow-up period. And you only see a minority of the people who've been vaccinated with Pfizer receiving a second vaccination during follow-up. But none of that is important to this talk. So what's going on here in terms of a randomized trial? Well, eligibility really was determined by your age group and other priority characteristics, such as being a healthcare worker or it being resident in a care home. So, for example, the 80 plus people in the top slide are in the UK priority group too. But eligibility doesn't coincide with when you get vaccinated. What really happens is that you define a group of people as eligible, and then on any day, those not yet vaccinated might choose to be vaccinated. So a hypothetical target trial that better matches the available observational data can be conceived of as a sequence of sub-trials, where on each day, eligible individuals who haven't yet been vaccinated are randomly assigned to the vaccination or no vaccination group and then followed until, well, if our outcome is going to be a diagnosis of COVID-19, then the follow-up will be until the earliest of COVID-19 diagnosis, death, or end of study period. And then a new sub-trial in this sequence starts on every day during the vaccination campaign. And then the estimates from each sub-trial can be combined once we've finished doing our sequence to obtain overall estimates of the risk of COVID-19 in each group and of the intention to treat effect. Now, I mentioned the intention to treat effect. That was another innovation in Robin's Eye carried over into ROB2. And again, just to remind you, the intention to treat effect is the effect of assignment of intervention. For example, the question of interest to a policymaker about whether to introduce a screening program. So I assign people to be vaccinated, or I assign people not to be vaccinated. I follow them up, and I don't worry about what actually happens subsequently. I just estimate the effect of assignment. And in both Robin's Eye and ROB2, we make a contrast between the intention to treat effect and the per protocol effect. The effect of adhering to the intervention as specified in the trial protocol. So, for example, if I'm thinking about whether to be screened, I don't want to know about what happens on average to a bunch of people that are invited to be screened, many of whom don't get screened. I want to know what will happen to me if I adhere to the protocol for screening. So that sequential approach has been adopted in some observational analyses of the effect of COVID-19 vaccination. And here's the paper by Dagan and colleagues published in the New England Journal of Medicine very rapidly, based on data from Israel, where, as you know, they were the first country to do mass rollout of COVID-19 vaccination from December 20 to February the 1st, 21. And Dagan and colleagues used this sequential approach. So every time somebody was vaccinated, they matched them in a one-to-one ratio with an unvaccinated control and followed them up. And then, so follow-up was from the time of vaccination for the vaccinated person and from that same date for the unvaccinated control. And then they followed them over time and looked at the cumulative incidence of SARS-CoV-2 infection and symptomatic COVID-19 and COVID-19 hospitalization and severe COVID-19, as you can see here. And you can go on to estimate relative measures from this. Now, an alternative version of this sequential trial approach way to describe the target trial is to consider vaccination as a time-varying variable. So we start follow-up at the time that everybody becomes eligible for vaccination. And in the UK, for people aged 18 and above, that would be the 8th of December 2020. And at that time, everybody is unvaccinated, and we follow them over. And then we switch them from we switch them from the unvaccinated group to the vaccinated group on the day that they're vaccinated, and then we follow them up. And we obviously need to control for confounders. And here, the confounders at baseline will be the confounders that we can measure on or before the date of eligibility for that group, which for the over 80s was the 8th of December 2020. And we can then fit a Cox proportional hazards model that adjusts for these baseline confounders and the time varying vaccination variable. And that allows us to estimate the hazard ratio for vaccination versus no vaccination. And that's been done in a number of the studies, some of which Julian quoted a little while ago. Note that, of course, you wouldn't, it's not immediately obvious that in these studies, what the target trial they imagine they're emulating. But this is kind of what they're doing, or this is what they're doing. Okay, so what are the methodological issues when we try to use observational data to emulate one of these target trials? Well, I've already mentioned the rapid uptake of vaccination, and I've already shown you this slide, so I don't need to talk to you about it again. But of course, the problem here is that unvaccinated people are rapidly vaccinated. So the number of unvaccinated people decreases rapidly over time, and that's got two implications. When we're using the sequential trial emulation, the pool of eligible people will rapidly become small for the later subtrials. Correspondingly, using the model with time-varying vaccination, hazard ratio estimates at a later time will be based on few unvaccinated people because there aren't many left. More importantly, many people assigned to be remaining unvaccinated in one of our daily sub-trials will be vaccinated soon afterwards. And that means that intention to treat effect estimates may be uninformative. Because if I take somebody who's vaccinated, for example, on the 2nd of January 2021, and I match them with an unvaccinated person, what I'd like to do is to follow them both over time from that point onwards. But then my unvaccinated person may be vaccinated on the 8th of January. In the intention to treat approach, I'd say, well, I don't mind, I'm estimating the intention to treat effect. But that intention to treat effect may be pretty much uninformative, because all I want to know is what is the effect that was estimated in the original vaccine trials? What's the effect of being vaccinated compared with not being? 2020, when those trials were being conducted, you couldn't get a COVID-19 vaccination other than if you're in a trial. So everybody who didn't get the COVID-19 vaccination remained unvaccinated. So an alternative is to try to estimate the per protocol effect by censoring people in the no vaccination group at the time they were vaccinated. And that's what Dagans et al. Did in the paper in the New England Journal of Medicine. They followed the pair, the vaccinated person and the unvaccinated person. And when the unvaccinated person got vaccinated, they censored both individuals so that follow-up was the same in the vaccine groups and the unvaccinated group. When estimating hazard ratios using the model with time-varying vaccination, that censoring is built in because people stop being followed as unvaccinated at the time of vaccination. So implicitly, when we use time-varying vaccination, we are estimating the per protocol effect, not the intention to treat effect. Okay, so the second methodological issue is that, as you all know, outcomes, COVID-19 outcomes, have varied rapidly in each country and differently in each country during the pandemic. So here's, I mean, you can download these sorts of plots online. Here's one I downloaded for the United States, where incidents went up and peaked in August, went down again, and then peaked hugely in December and January, December 2020 and January 21, went down again, up a bit in April, went down by June, and then went back up again, as it has in many countries, as following the vaccine rollout, social distancing measures were relaxed. So when the incidence of the outcome is varying so dramatically, it becomes absolutely vital to ensure that we are allowing for this variation with calendar time when we look at vaccine effectiveness. Rapid changes in incidence make it essential that analyses account precisely for calendar time. Now, when using the sequential trial emulation approach, that adjustment is built in because follow-up for vaccinated and unvaccinated individuals starts on exactly the same date in each subtrial. So you're balancing things out because in a one-to-one matched approach, they're both vaccinated on the same day, they're being followed up over the same calendar time period. You can also do that in the approach with Cox models with fixed baseline date and time varying vaccination, if you set it up correctly, because then hazard ratios are estimated using risk sets, comparing outcomes in vaccinated and unvaccinated individuals on the same date. But that precise matching or allowing precisely for the incidence according to calendar time is essential for observational studies of COVID-19 vaccine effectiveness. So the third issue, and of course you all know this, is confounding, the presence of characteristics predicting both vaccination and outcome. And we can split that into baseline confounding and time-varying confounding, which I'll come to a little bit later. So as you all know, confounding occurs when there's a common cause of both vaccination and the outcome event. And well, such confounding is clearly present. So here we've estimated hazard ratios for vaccination with Pfizer, BN.2.162b2, or AstraZeneca, ChAdOx1, in people aged 80 plus and in people aged 70 to 79. And you can see that there are strong relationships with of risk factors with vaccination, and they're not all consistent either between age groups or between vaccines. So in the older people were more likely to get Pfizer, but not more likely to get AstraZeneca. In those aged 70 to 79, they were less likely to get Pfizer, and older people were more likely to get AstraZeneca. Less deprived people were more likely to be vaccinated. People in ethnic minorities were less likely to be vaccinated. People with learning disabilities were in general less likely to be vaccinated, although not with AstraZeneca in the over 80s. And people who previously had a flu vaccine in the previous 5 years were notably more likely to be vaccinated, and so on. So clearly there is baseline confounding. What about unmeasured confounding? I mean, all these analyses have been done using electronic health records, which are designed to facilitate healthcare, not the conduct of research studies. And it's important to bear in mind that important confounders may be incompletely recorded or omitted altogether. And one particular example is that, I mean, certainly in the UK, when you show up for vaccination, there are big notices everywhere saying, please go away if you have respiratory symptoms. So presence of respiratory symptoms greatly reduces the probability of vaccination in unvaccinated people and increases the probability that you get diagnosed with COVID-19. But certainly in the UK, those symptoms were not recorded. The fact that you postponed vaccination was not recorded, although they did a great job of recording the vaccinations that actually took place. So data on mild symptoms are rarely available. So observational analyses can only adjust for proxies of the presence of symptoms. Dagans et al., for example, did that by restricting analyses to people without a recent contact with the healthcare system, which could have been triggered by respiratory symptoms. Just a word about test negative designs. They're not really the subject of this talk, so this is slightly parenthetical, but a number of authors have used test negative designs comparing individuals with symptoms who tested positive with those who tested negative. And that may plausibly reduce confounding, but it may also have other unexpected consequences because you are conditioning on being tested, and you may be conditioning on a common cause of the outcome and the exposure, and that may introduce selection or collider bias. So here are a couple of papers about that. I think we're still struggling to know or to understand the extent to which these designs have removed bias compared with the follow-up designs that are the focus of this talk. So careful evaluation of the potential for bias in these designs seems warranted. So finally, I want to turn to time-varying confounding. And that problem is that after baseline, for example, after the rollout started in people aged over 80 on the 8th of December 2020, time-varying factors may influence both the probability of vaccination and the risk of the outcome. And these time-varying confounders also need to be adjusted for when we're estimating the per protocol effect. So the issue is that that we start follow-up, for example, on the 8th of December 2020, there's some time unvaccinated, there's some time vaccinated. And now the confounding is not just at baseline, we can also have post-baseline or time-varying factors that should also be adjusted. And special methods such as marginal structural models are likely to be needed when there are time-varying confounders. So, and the point where you need the special methods if the time-varying confounders are themselves influenced by vaccination, in which case there's time-varying feedback between vaccination and the confounders, and then standard methods, Cox models, are usually not appropriate. Once again, the definition of time-varying confounding depends on the analytic approach. If we're emulating sequential trials with time-fixed vaccination, baseline confounders vary across the sequential trials, but they are fixed and updated for each trial. So if my vaccinated person is vaccinated on the 15th of January, my baseline confounders are everything that I can measure up till the 15th of January. But in the hazard ratio approach, using models with time-varying vaccination, anything measured after baseline is a time-varying confounder. So there are clearly also time-varying characteristics predicting vaccination in the English data that we've analysed. And in particular, we looked at time since a positive test. And broadly speaking, individuals who'd had a positive test in the previous 3 weeks were some 90 or more % less likely to be vaccinated. Broadly speaking, you weren't going to get vaccination if you had recently tested positive. Sorry. And that turns out to be really important in the time-varying approach when you estimate vaccine effectiveness. So this is a busy slide, but I'll quickly take you through it. So the green points are region-stratified Cox models with no further adjustment. Orange is adjustment for all the baseline confounders, which you can see makes some but modest difference. And the blue is adjustment for both baseline and time-varying confounding. And when we look at that, the first thing we can see is mortality, adjustment for the time-varying confounding, adjustment for the fact that people who'd recently had a test were hugely less likely to be vaccinated, made a really enormous difference to estimated efficacy. Secondly, you can see that we got completely implausible apparent benefits of vaccination, particularly in the first week after vaccination. And since I think for both biological reasons and consistency with the trials, it is absolutely implausible that there was any substantial benefit the first week. That suggests that we've got substantial unmeasured confounding in these estimates. For example, because people with respiratory symptoms were much more likely to develop COVID-19 and much less likely to be vaccinated, and that simply wasn't recorded in the data. Thirdly, we would like to believe that later on in follow-up, you can see that estimated efficacy went down, perhaps as the biases I've talked about dissipated. But then later on, we get estimates of efficacy of around 50%, 60% efficacy that we would like to believe. But the worry there is that how much residual bias, given that it's clear that some of our estimates have got profound biases, we don't know whether the later estimates are still affected by those biases. And a final point is to say that these days we're interested in long-term effects, and the problem we've then got is that there are a very small proportion of persistently unvaccinated people to compare with fully vaccinated people, as you can see. We're mainly now interested in vaccine efficacy some weeks after receipt of the second dose, and the only people we've got left to compare them to is a very small proportion of people remaining unvaccinated. And we should be concerned about whether people remained unvaccinated because of recent infection that may also have conferred, in which case we may get completely the wrong answer on efficacy. So we've been looking a little bit, as you can see in this table, at the persistently unvaccinated, that's not vaccinated 12 or more weeks after you became eligible for vaccination. Firstly, it's a very small proportion of the older people who remain unvaccinated, and the confounding is pretty clearly even bigger. So hugely, Black and South Asian people are much less likely to be vaccinated. People with prior flu vaccination are much more likely to be vaccinated, And people, and actually the COVID test, it went the other way. So in the 50 to 54-year-olds and 39-year-olds, people with a positive COVID test before eligibility were much more likely to get vaccinated. So the vaccines work brilliantly, but there are really difficult issues in using observational data to guide policy. It's very hard to estimate vaccine effectiveness in the rollout, and we need careful and critical evaluations of designs and analysis strategies, comparing estimates from different approaches. And I think considering effects on negative control outcomes, such as non-COVID mortality, hasn't been done enough and should be done so that we can understand whether our estimates are plausible. Thanks for your attention.
Thank you very much, Jonathan, for a very informative talk. We're running a bit late, but I think that if it's okay for people to stay just 5 minutes more, I'd really like to hear any questions or comments. Well, while people might think of some, I'd like to ask you, Jonathan. I mean, you're focused on efficacy of the vaccines. Could you comment on kind of harm aspects of vaccines here? It's a delicate issue, I know, but
yeah, well, so similar issues arise when you're. I mean, the same sorts of target trial issues arise regardless what your outcome is. My hope would be that if you're interested in looking at BIT or myocarditis, the problems shouldn't be as great. I think the very obvious time-varying confounding that I showed you in the results slide happens because it's the COVID that influences, for example, recent positive tests that influences whether you get vaccinated and also influences mortality. So I think that's probably less of a problem. I think there won't be profound short-term changes in cardiovascular risk that influence vaccination. So I suspect the time-varying confounding is less of a problem. You still need to control baseline confounding.
any other questions or comment, Isabel?
Thank you very much for this great talk, Jonathan. Perhaps just one question. Did you have any thought about the policy related to test? Because, for example, in some country, anyone could get tested whenever they wanted. Now in France, you can get tested, but you have to pay. So what could be the impact on that?
Yeah. I suppose, I mean, broadly speaking, the implications of testing positive, the implications of testing positive will change in those epochs. So, you know, I mean, in the UK, testing was not widely available until, you know, September 2020. And so the meaning of a positive test is very different in spring and summer of 2020, when you only got tested if you showed up in hospital and you were really, really sick. And that has a very different, I mean, of course, that doesn't apply to the vaccine rollout. So mainly in the vaccine rollout, well, the vaccine rollout will have happened, most of it, in an era of freely available testing in many high-income countries. But the meaning now, when we come to look at boosting of positive tests, may change again, I guess. And so we might want to look at predictors of vaccination, that, you know, a test, the way that test predicts vaccination differently as testing policy changes.
Any more questions or comments? I have one additional last question for you, Jonathan. Focused on confounding and kind of classical approaches to bias in observational studies. Could you comment on the issue of reporting bias or non-publication of observational studies? I know it's not relevant with regard to your fantastic data material, but in general, pre-specification of outcomes in analysis versus published analysis and outcomes.
Well, a couple of points about that. I mean, there's a certain reporting bias. It took us so long to do these analyses because they were so many highly technical, because I insisted on doing a marginal structural model, that we're only ever going to be able to publish them in a methods paper because nobody cares anymore about the impacts in the first few weeks of vaccination. So in one sense, that's a reporting bias. So I think the stuff that got published quickly, people just got it done, and may not, and that's why assessing the risk of bias is important. But I mean, there's also been profound changes, I think, in the last 18 months in the way that we think about reporting observational data. And I've certainly learned a huge amount about posting protocols in advance on GitHub. I think the extent to which people are analyzing electronic health records, are making their code transparent and posting protocols in advance, it is a really profound change for the better, and will change the way we think about reporting biases in observational studies. And I hope that will be a permanent improvement subsequent to the pandemic.
Great. Thank you.
Jonathan, I have a question. It's Ian. How did you deal with the fact that, or did you, with the fact that people, when they get vaccinated, change their behavior, but you also have just policy changes, like here in Montreal, certain points the city opens up and we can go to restaurants and we can't go to restaurants, and then there's individual behavior related to that. Did you try and address that, or it's just you kept it simple?
Well, it's not so much that you kept it simple. It's a question. I mean, I think it relates to what is your effective interest. So, the second point, Ian, the policy changes. I mean, that's yet another example of why it's essential that everything is matched exactly on calendar time, because you simply cannot compare an unvaccinated person followed during a period of imposition of social distancing with a vaccinated person followed after social distancing was relaxed. They're just not comparable. Everything must be done exactly on calendar time, and that's just one of the reasons why. The point about does it matter about behavior change is I think I would say that that's just part of the effective interest. If one thing that happens after vaccination is that people behave, take more risks than they would otherwise have done, I'm not sure that we need to estimate the effect of vaccination had everybody's behavior remained the same. It's just part, I would say that's part of the effect. In other words, the trial protocol does not say your behavior must remain the same. Although in a placebo trial or in the early trials, maybe that's the distinction. In the early trials, people didn't know what they got. So their behavior, any behavior changes were balanced between the groups. But in the observational studies, behavior changes is just part of the effect of vaccination and cannot be adjusted.
So I would just argue that the direction of that would be to minimize the effectiveness of vaccines on a theoretical basis. So if you see an effect, then the vaccine is at least that effective. Because the people
compared to the effect you're imagining, compared to the effect that you're imagining, which is the effect in the absence of behavior change.
Right. So just because if you think about the anti-vaccination crowd, they'll say, oh, they'll just see a bias. And they'll say, oh, I don't believe the study. By telling them which direction that bias would affect, you actually counter their arguments. This is in my head anyway. I don't know if it's true.
I'm just being a bit reluctant to call that bias. I just say that, but I agree that the effect estimated in these observational studies, which incorporates the behavior change, will be towards the null compared to the effect in the absence of behavior change. I'm just not going to call it a bias. But I completely agree with your point.
Okay, we're running 6 minutes over time. I think unless there's a pressing need for a last question, I'm going to thank Jonathan and Isabel and Julian for great talks, and you, Kraut, for very good company and questions, and close the meeting. Thank you very much, everybody.
Thank you.
Thank you.
Bye-bye.